Hi, I'm Dr. Bob. Normal operation of Yuasa motors and test jigs is to stop at one end of a cycle to make a test measurement. Either end can be selected. Examples for measuring when a sample is stretched, or when a sample is flat, or when stretching is relaxed. I usually refer to this topic at measuring at both plus SP and at minus SP, where plus SP and minus SP are the cycle reversing positions. In this case, that's plus SP minus SP. It's at minus plus SP, minus SP, plus SP, minus SP, plus SP. Using flex data though, there are techniques you can use to make a measurement at both ends of a cycle. You can see that with the test that I am running right now. After running a couple of cycles, the jig stops to make a measurement when the sample is not compressed, there, and then moves to the compressed and takes a measurement, and then runs cycles again. And then the next cycle, it stops to make a measurement here, that's at minus SP, at plus SP is measurement, and then runs cycles again. In this video, I will show you how I use flex data to make measurements at both ends of a test cycle, and how I can make multiple stops during a cycle for measurements. First, I will show you a flex data algorithm for the DR11MR to automatically stop and measure at both ends of a cycle, and I will run a test to illustrate it. Then I will show you a similar flex data algorithm for the DM-LHP to stop at both ends of a cycle, but it requires operator intervention to make changes during every measurement period on the HP touch panel. And again, I will run a test to illustrate it. Then I will show you a flex data algorithm for the DR to make multiple stops during a cycle for measurements. Once again, I will run a test to illustrate it. In the flex data setup video, I did have a chapter on measuring at both plus SP and minus SP, but I will show you more details and possibilities in this video. You might want to watch that video before watching this one, but it is not a requirement. I will run a test using the FS Dacian, a multi-purpose jig that can fold, stretch, and compress by changing accessories on the moving and fixed sliders. This is the FS Dacian, and we're running in the compression mode. This is the fixed slider, that is the moving slider, and this is the FS Dacian jig. In these tests, I will use a load cell to measure squeezing force on a tennis ball. This is the load cell. It's inside this little box. With the load cell, you need an initial no-load measurement to calibrate the test for calculating load. I will want that measurement to be made inside the flex data algorithm, so it is a part of the overall measured data. At the end of the test, I will make another no-load measurement for completeness. I will go through each of the steps during this video. I will be using screen recording so you can see the computer screen. I will be using a live camera looking only at the tennis ball, so flex data can record snapshots of the tennis ball when every measurement is made. This is the camera that's looking only at the tennis ball. I will have an overall live camera to give a greater view of the test setup. That's the camera we are viewing right now. During the HP portion of the video, I will be using an additional live camera to look at the HP touch panel so you can see exactly which buttons I am touching on the touch panel. Let's look at the DR algorithm. The top 5 lines are comments defining the test. We will start with minus SP set for 5 degrees and plus SP set for 45 degrees. That might seem funny. We are setting degrees where we're actually working in millimeters. With the DR linear converter, which I am using, the settings must be in degrees converted from millimeters. I want to compress the tennis ball about half an inch, 12.7 millimeters. The conversion factor is 1 millimeter equals 3.183 degrees. So I will be compressing 40 degrees, which really means 12.57 millimeters. In our test setup, we will set the fixed slider to ensure that the tennis ball is just touching the compression plates when minus SP equals 5 degrees. This is our minimum compression position. Plus SP equals 45 degrees will be our maximum compression. The compression will be about 80 newtons. The 3 brown blocks specify the test equipment we will use. First, the DR11MR, then a Keithley DMM6500 which will be set to be a digital multimeter measuring the voltage output of the load cell. And a Logitech C920E webcam will be used to get a snapshot when each measurement is made. There are 4 loops in the algorithm. Here's one, here's a second one, here's a third one that's actually inside the second one, and the fourth one. Let's look at the second loop first. This is what I call the test loop. The loop will repeat 5 times. The test is basically the first line in the loop instructing the DR to run 4 cycles at 100 degrees per second, which is about 31 millimeters per second, about 37 RPM. That instruction is followed by what I am calling the measurement loop. The measurement loop will run 1 time, then the repeat will go back up to the moving the DR several cycles. Let's take a look at the measurement loop. There are 3 lines. The first and the third instruct the measuring equipment to do their things. The first will measure when the tennis ball is not compressed, and the second will measure when the tennis ball is fully compressed. The line between the 2 experiment records is used to move the DR from the minimum compression position, which it will be coming out of this loop, and we want to move it to the maximum compression position. So we set plus SP and minus SP both to be 45 degrees. This will make the actual reading occur at 45 degrees. The pre-test measurement loop will start by making the very first voltage measurement with the tennis ball not compressed. Then the DR will move 1 time to reach plus SP to make the maximum compression measurement. Notice again that we set both minus SP and plus SP to be 45. Now we can look at the last loop, which I call the post-test measurement loop. The last measurement in the test loop was at plus SP with maximum compression. I want the very last measurement to be another no-load compression, so the DR will move to the minus SP position, and I have set both plus SP and minus SP to be 5, and then the voltage measurement will be made. I make this measurement for completeness. The no-load voltage should be very near the same value as the original no-load voltage, but I just like to check it. Next, we will look at the FS-N jig to see the jig setup. As I said before, this is the fixed slider, and this is the moving slider. And as I pointed out, I'm using the load cell clamp on this end. Normally you use this clamp for a sample for stretching and measuring tension. In my case though, I'm pushing the tennis ball against the clamp and measuring the compression. The load cell in the clamp is a tension compression load cell. It can measure both. And as I said, this is the moving slider. The accessory I'm using on this slider is the accessory that's used for folding and compressing. The moving slider is connected to the motor so it can be pulled toward the motor to the minus SP position and away from the motor for the plus SP position. This metal block is something I use to center the tennis ball on the load cell clamp. Down in the bottom is another metal block that I'm using to lift the tennis ball so that it's centered exactly on the load cell clamp. I'm going to pan the camera. This long screw with 2 knurled nuts is used to position the fixed slider. Before the test begins, I will use the knurled nuts to position the fixed slider and thus the tennis ball up against the moving slider. I will want the tennis ball to touch but not push. This will be for my no-load measurement. Let me begin my setup of the test. First, I will set the position of the fixed slider. I'm using a Keithley DMM 6500 to measure the load cell voltage. I'm using an app to show a continuous measurement of the voltage. At the moment we're on the settings page. Let me go to the recording page. here's a graph, and you'll notice that it's running at the moment 67.89 as a value, and it's very noisy, and that's because we're really looking at tenths of a microvolt here. So I'm going to start tightening the inside screw. I'll loosen the outside so I can move it. I'm going to tighten the inside screw to put compression on the tennis ball. And watch the meter. I'm going the wrong direction here. Watch the meter. 69, 70, 72, 73. See how I'm increasing it? Let me take it back again. It's going to drop now. 70, 69, 68, 67, 66, and it won't, 65, but it won't go any lower because I've totally moved away from the ball. Let me tighten it up to be about 66 or 67 microvolts. Okay, that's 67 microvolts. So I'm putting just a slight amount of compression on the tennis ball. And that's the way that I will use it in the test. Before I begin the DR test, let me explain the calculations for the load cell. I will make a no-load measurement at the very beginning. That voltage will represent no load on the tennis ball. What we need from every measurement after that is the difference in the measured voltage, V sub x, and the no-load voltage, V sub no load. That difference will be divided by the sensitivity factor of the specific load cell being used. For my specific load cell, I have previously determined that the output voltage will change by 46 microvolts for every kilogram of load applied. When I divide the difference voltage by 46, I will know the load in kilograms. For the test that we're going to be doing with the DR, I already know that the no-load voltage will be about 65 microvolts. I know that the maximum will be about 465 microvolts. Therefore, the difference will be 400 microvolts, and divided by 46 kilograms means that it'll be about 8.7 kilograms, the equivalent of 8.7 kilograms of force. And if we multiply that by 9.8 to get the load in newtons, that will give us about 85 newtons. But we'll see later on both at 65 microvolt and 465 microvolts and the 85 newtons. Now I will run the DR test. I have set the DR for the starting conditions. I will click on Execute to begin the test. It immediately makes the first measurement to get the no compression voltage, which is 75 microvolts. And then it very rapidly makes the first maximum compressed voltage measurement, and that is, it looks like it's 537 microvolts. Both numbers are a little higher than I had predicted earlier. And so we run all the cycles, then make the measurements. Run the cycles, make the measurements. You can see the no-load voltage on the graph and the loaded voltage. And this is like a triangle wave. You can see the tennis ball on the top right as it's being compressed. This is the FlexData app. When the test is over, the tennis ball will disappear. Okay, the test is over. In the center of the screen, you see a table showing the values through the test. The time, the position of the DR, the voltage that was measured each time, and the angle where the measurement was made. The algorithm shows, the equipment that's being used shows, and the graph shows. Plus snapshots from that of the webcam every time the measurement is made. This was not compressed. This was a compressed. You can see that the tennis ball was compressed. So this is the record that you're making of the test in FlexData. As I said at the beginning, for the DMLHP to stop at both ends of a cycle, operator intervention is required to make changes during every measurement period on the HP touch panel. For the HP test, I will add a slight variation. During the test, I want to keep compression on the tennis ball during the entire test. To do this, I will set -SP greater than the no-load condition. You will see that the HP algorithm is longer than the DR algorithm. There are two reasons. First, I will be making more measurements because the minimum compression during the test is different from the no-load measurement, which I have to make at the beginning and the end of the test. And second, I have to insert alert blocks for the operator interventions. Some other differences in the HP test will be load. With the DR, the maximum load was about 9 kilograms force, or about 90 newtons. It will be lower for the HP because the maximum specification for the HP is 72 newtons, so we will have to do less compression of the tennis ball. Let's take a look at the HP touch panel. The significant difference in the DR test and the HP test is that I, as the operator, must touch buttons on the touch panel throughout the test because the HP does not allow remote control of +SP and -SP. This means that I will need to change both +SP and -SP during the test. Touch position, and you can see the settings for -SP and +SP. -SP is 109, +SP is 120. And I will need to change the stop position among its three possibilities, plus or 0 or minus. Touch settings, and you can see the stop position. Right now it is set on plus. Back to the home page. This can be done automatically in FlexData with the DR11MR motor unit, but not with the DM-LHP motor unit. With the HP, I must make manual changes in those parameters when using the touch panel, and the HP cannot be in motion when the change is made. Just as I did in the FlexData setup video, I will place an alert. So here's an example of an alert. In the algorithm, each time I must change something on the touch panel. You'll see there are several alerts in here. The alert will stop the motor until I click on continue. Let's look at the different blocks in the algorithm. The top 4 lines are comments defining the test. We will start with +SP set to 120 millimeters. In our test setup, we will set the fixed slider to ensure that the tennis ball just touches the compression plate. We will use +SP equals 115 millimeters for our minimum compression, so the tennis ball will always be subjected to compression test. We will use -SP of 109 for our maximum compression. Altogether, the compression will be 11 millimeters, which is near the maximum of 72 newtons for the DM-LHP. The 3 brown blocks specify the test equipment we will use. First, the DM-LHP. A Keithley DMM6500 will be set to a digital multimeter, and it will measure the voltage output of a load cell. And a Logitech C920E webcam will watch the tennis ball being compressed. There are 4 loops in the algorithm. Let's look at the second loop first. And this is what I call the experiment loop or the test loop. The loop will repeat 5 times, and the basic instruction is this brown line, which is moving the motor at 30 RPM for 4 cycles. The instruction is followed by what I am calling the measurement loop. The measurement loop will run 1 time, then go back up to the line instructing the DM-LHP to run the second set of samples. Let's look at the measurement loop. There are 5 lines. The first and the fourth instruct the measuring equipment to do their things. There are 2 of the experiment records. The first one will measure with the minimum compression, and the second one will measure with the maximum compression. The 2 lines between the 2 experiment records are used to move the DM-LHP, because we'll need to move it from the minimum compression record point to the maximum compression record point. The alert line will ask the operator to use the DM-LHP touch panel to set the stop position to minus, which will cause the DM-LHP to move from its current +SP position to the -SP position to make the second measurement. After that measurement, there's another alert to tell the operator to use the DMLHP touch panel to set the stop position to plus, which will cause the DMLHP to make its next stop at the stop position plus SP. After the alert is cleared by the operator clicking on continue, the next step in the algorithm will be the second set of the five cycles for the test. Now let's go back up to the first loop, which I call the pretest loop. The first measurement, the experiment record, will be made before the DMLHP starts up, which is the tennis ball not compressed. We need to make that measurement because the load cell calculations require that we know the no load voltage. That's the first measurement that is made. Then the DMLHP will move one time to reach minus SP and make a measurement. This will be the first minimum measurement. The next line is another alert for the operator to set minus SP to 109 and set plus SP to 115 for the actual test. The operator will make these changes using the touch panel, and then the DMLHP will move to the maximum compression position and measurements will be made at this point. This will give us the very first maximum compression voltage. The next alert tells the operator to change the stop position to be plus, so the machine will stop at plus SP whenever it completes the first cycle of the test. Now we can look at the last loop, which I call the post-test measurement loop. The very last measurement in the test loop was at minus SP with maximum compression. I want to get the very last measurement of the minimum compression, so the DMLHP will move to the plus SP position. That was the last instruction in the test loop. Then the DMLHP will stop and this measurement will be made. The next line is another alert to have the operator change plus SP to again be the no load position of plus SP equals 120 millimeters, and the minus SP will be changed so that the DMLHP will start from its current position, which is 115 millimeters, and not go back to the 109 millimeter position, but go directly to the 120 millimeter position. Once the DMLHP reaches that position, it will stop and the final measurement will be made, which is a no-load measurement. I do that for completeness. The no-load voltage should be very near the value of the very first no-load voltage before the test began. Now I am ready to begin the flex data test. Throughout the test, I will be going back and forth between the computer and the touch panel to set values on the touch panel, and then back to the computer to click on continue. Let me start with the flex data algorithm. This is the algorithm that we looked at before. I need to make sure that SP is at 120 and minus SP is at 115, and we have a minus. So let me go set that on the touch panel. It's 120 and 115 and minus. I'm going to click on execute. We're waiting for the camera to lock on. And I've already done the first two measurements that I talked about. And I've already had the first alert that says I need to set minus 109 and 115. Okay, I've set the 119, the 109, and the 115. And I'm going to come back to the computer and I'm going to click on continue. And we ran that one half cycle, and I have to now set plus. Let me go back to the computer, to the touch panel. I'm going to set plus. I'm going back to the computer and I'm going to click on continue. Okay, the test is running those first 4 cycles. This colored position block shows where we are in the algorithm. Okay, we just moved beyond that and we're into the alert. I have to go set minus. Back to the computer to click on continue. And it's going to make the second measurement and it's going to tell me to go to set plus. Let me go set the plus. Back to the computer to click on continue. And now we'll go through the second set of 5 cycles. I thought I had that set for 4, but it's actually 5. I'm going to repeat 5 times with 5 positions inside. Okay, we're back on the set minus. Back to the computer and click on continue. It's going to ask me to set plus. Back to the computer to click on minus, to click on continue. And it's going to run the next set of 5 cycles. The next thing that will happen is that I'll have an alert to set the minus. There's the alert. Set the minus. Go back to the computer and click on continue. It's going to ask me to set plus. And back to continue on the computer. After you've done this a time or two, this will come much easier than it seems right now. And it's taking me a long time because I'm documenting every step as we go along. Okay, I think we're going to hit this alert again. Got to set a minus. Back to the computer to click on continue. It's going to ask me to set the plus. Back to the computer and click on continue. And now it's going to run 5 cycles again. And make the minimum compression measurement and then tell me to click on minus or to set minus on the touch panel. So back to the touch panel. I set the minus. I'm going to click on continue. It's going to tell me to set the plus. Back to the computer and click on continue. Oh, and I see that we have actually gone into the final step now where I'm making those final measurements. And now I need to change SP to 120 and 115. 120 and 115. It's home, position, and plus SP will be 120. And minus SP will be 115. And then I click on continue. And it does that final move and the final experiment record. And now the test is over. The camera always disappears when the test is over. So we have completed this test. Let me just run through a couple things with you here though. I want to look at the table, but I'm going to go to the full table chart here. There are many lines in this table, and the number of lines has actually tripled because for every iteration, here are the iterations, for every iteration, there's a start alert and an end alert. Notice this is the start alert and an end alert. Yep. This alert said set minus, and it ended when I clicked on the continue button. So many entries in the table. The number of iterations is doubled because for every measurement there are 2 steps. So I had set this for 5 trips through the test sequence, but we have 14 different iterations here because they increased because I have to make 2 steps for every measurement. Let's look at the DAQ values. At the very beginning, I had 69 microvolts. That's what we started with, 69 microvolts. And that first measurement compressed said 153 microvolts, 154. And the first full maximum compression said 334 microvolts. Then from that point, the minimum number was 85 microvolts, then 82 microvolts, 80 microvolts, 80 microvolts, so that varied. The maximum microvolts in this first case was 334, then 324, then 322, then 319, and see it's decreasing slightly because the tennis ball is getting compressed and it remembers a little bit of that. And then finally down at the very end, we have 68.66 microvolts, and this was 68.91 microvolts, very, very close. That is the no load measurement. Let's go back to the dashboard, and I want to look at some snapshots. Here is a picture. This was compressed. So here's a picture of the ball compressed. And this was the 85. This was the partially compressed. And I think I'm saying this wrong. This is the no compression at all. This is the partially compressed. And this was the fully compressed, as full as we're doing it. So you have snapshots of every time a test was run. I want to look at the graph. And clearly it's a sawtooth. This is for the starting point. This is for the partial compression. This is for the full compression. Partial, full, partial, full, partial, full. And the reason we have these bottoms here is because the motor was not moving, and that causes us to have no reading here. So the actual data is going from here to here to here to here to here to here. Let's go back to the dashboard. And the dashboard gives you the last results in the table, the most current results in the table. It tells you what equipment is in use, and when the test is actually running, there's a camera showing up there. The algorithm that you ran, and the chart, the graph. The algorithm for multiple stop and measure points is very similar to the other algorithms. The key difference is the test measurement loop, which you'll see is very large. The comments at the top are similar to comments that we have seen on the other algorithms. The equipment setup blocks are the same. The pre-test measurement loop is very similar, and the post-test measurement loop, which I don't even have here, would be very similar, except the very last measurement takes care of what I need. Let's look at the measurement loop in detail. In this case, I have set up 7 different measuring points. 1, 2, 3, 4, 5, 6, 7. I'm doing this to illustrate 3 different points. First, you can select any number of measuring points you want. Second, the measuring points do not need to be spaced equally. Third, you can have measuring points in both directions in the measurement cycle. The first measurement point is the not compressed measurement point. I do the one first though in the pre-test loop, but then in the measurement loop, the first measurement will be at at no compression. Then we'll move from the 0 position of 5 degrees to 15 degrees. That's a change of 10 degrees. Then we'll move another 10 degrees. And then instead of moving 10 degrees, I'm going to move 15 degrees. And then to the maximum, instead of moving the 10 degrees that I was doing on the others, it'll only be 5 degrees. So there'll be this point will be closer to this one in the measurement. The 5th one then is at the maximum compression point. The 6th one is going back down. It's on the other direction. I'm going to do that at 2020, which is halfway down. And then the 7th, I'll go all the way to the 5, SP plus of 5 and SP minus of 5, to be at the beginning point, which is no compression. Note again that for every stop and measure point, I have set plus SP and minus SP equal to each other and equal to the desired measuring point, whether that is 15, 25, 40, 45, 20, or 5. Now I will run the DR multiple stop and measure test. I will show the live camera in the upper corner so you can have a better view of the tennis ball being compressed and held at several different points. As I have done in all the other tests, I will get a not compressed and maximum compressed measurement before beginning the test. I click on execute to begin the test, and the test is running now. We immediately see the not compressed data line and very quickly also the maximum compressed data line. Voltages are 74 microvolts and 526 microvolts. We have moved into the test loop now. We are stopping at the multiple positions. That's minimum compression, 3 points on the way to maximum compression, then 1 on the way back to not compressed, and finally another measurement at not compressed. This will happen 5 times. We're doing the different steps now. And this is now finally the no compression, and we're off on the next cycle. Note the different appearance of the graph. While it is similar to the not compressed and maximum compressed graphs, it has a different appearance. The triangle does not go straight to the top. It has inflection points. You see that point, that point, that point, the top point going down, 2 bottom points going up. It has these points for the different measurements that are being made. Keep in mind that this graph is not a continuous graph. It is simply straight lines drawn between successive measurements. And the tennis ball will disappear soon because this, I believe, is our last measurement cycle in the test. No, there's one more cycle left. Stopping at the different points. That was the maximum compression, half compressed, no compression, and now it's over. And that's the end of the update of the FlexData Setup video. In this video, we went deeper into multiple measurements during a cycle. With the HP, we have to make manual changes on the touch panel every measurement period. But with the DR, we can program all those stops and no operator intervention is required. And the DR gives even greater test possibilities by allowing multiple stops during each measurement cycle. And all this is automatic in the algorithm. The operator can start the test and leave during the test.